something.
Uh-huh.
When objects fall, like free fall,
Mm-hmm.
the acceleration is 9.8 meters per second squared, right?
Yeah.
So why don't feathers drop at that rate?
Good question. Maybe it's because of the drag from the air resistance.
That might actually be it.
You know what? We should test this out.
Let's get to it.
We know that in free fall, objects fall at the same rate of acceleration, 9.8 meters per second, regardless of their mass. But why do things like feathers fall slower then? Could this be the work of air resistance or drag? The only obvious difference between feathers and regular objects are that feathers have a notably lighter mass. Does this mean mass has an effect on air resistance? For our culminating, we are going to investigate drag on objects with different masses to see how they compare.
In order to do this, we will attach a parachute onto an object and drop it at a controlled height in a controlled environment 10 times. We need a parachute because we want to get a calculable amount of drag relative to the object so that it will be significant. So that we don't change the surface area of the object and add or take away air resistance, we will use a water bottle as our controlled variable. We will add 50 milliliters of water each time and calculate the mass of the water bottle and the water each time.
In order to make sure we always drop the water bottle from a constant height, we taped a tape measure to the ceiling to make sure that we knew where to start.
Wait, now what?
We should put our data into a tracker so that we can get the most accurate answers.
Alright, let's do it.
So then, after countless hours of working hard in Tracker, we were able to find the change of time and the acceleration of each of the drops. Using our results, we were able to fill in a chart. Seeing the information we had, we were able to figure out what we needed to do next in order to answer the question, how different masses affect the drag force. If you draw a force diagram, you can see that there are only two forces acting on the bottle in the air, the force of gravity and the drag force. Therefore, all we need to find is the drag force and compare it to the mass. In order to find the drag force, we would need to use this equation. If F net is equal to force of gravity plus the drag force, then the drag force would be equal to F net minus force of gravity. Using this chart, I can then find the values for F net for each of the masses and then plug it in to solve for the drag force. Creating yet another chart, I know that force of gravity is mass times gravity. I already have all the values for F net, and I know the formula for the drag force. In this case, we are assuming the positive direction is up, therefore all of the forces of gravity will be negative. Finally, I have made one final chart comparing mass directly to the drag force. I have also made a graph to see if there is any trends in our results. Unfortunately, there doesn't seem to be any obvious trends in this graph, as the points are kind of not in a line. pretty random. It goes like up, and then it goes down, then up again, then down. However, there does seem to be a peak right at the tip of our curve of best fit. That is where the drag force was highest at 262.7 grams, and then from then on it just goes down. Of course, our result could have been more accurate due to possible errors that we could have made, such as the timing of release of the bottle, which is a human error, or small damages to the parachute we could have not noticed, such as shape changing after a few drops, or the fact that the force of gravity on the bottle could have been different since we're not in a vacuum, so there could have been actually air resistance on the bottle itself.
So now we know how air resistance works, huh?
Yeah.
Wasn't that fun?
No, that was a lot of work.
That was educational though.
Yeah.
Whatever, it was fun working with you though.
Yeah. Good job.